Hey everyone, welcome to this explainer. I am thrilled you're here. Today, we're putting on our hard hats and stepping right into the shoes of a professional robotics control engineer. Our ultimate goal? Ensuring smooth, intent-driven robotic movement and preventing catastrophic million-dollar errors on the factory floor. To do that, we have to master the absolute foundation of robot motion, kinematics. Here is our game plan for today. We'll hit 1. Motion without the force. 2. Forward kinematics, finding position. 3. Standardizing with the DH convention. 4. Inverse kinematics, reaching the target. 5. Differential kinematics and velocities. And finally, 6. The Jacobian, preventing real-world errors. Let's get to it.
Kicking things off with Section 1, Motion without the force.
So as control engineers, our absolute first job is to simplify the problem. We literally have to ignore force, torque, and mass altogether. It's kind of counterintuitive, right? But instead, we look purely at the geometry. That's kinematics in a nutshell, studying the geometric relationships between a robot's links and joints. Because out there on an operational factory floor, understanding this pure motion geometry, that is step 1 to preventing any physical motion errors.
Moving right along to Section 2, Forward Kinematics, finding position.
Forward Kinematics, or FK for short, gives us one highly straightforward mathematical solution. Think of it like this. If we already know the exact angles of our rotational joints or the displacements of our sliding joints, we can figure out exactly where the robot's end effector is. We do this by simply attaching a coordinate frame to every single joint.
And here is our mathematical translation software for mapping from one joint frame to the next. It all relies on a 4x4 homogeneous transformation matrix. Now looking inside this matrix, that 3x3 rotation matrix up top defines the physical orientation, while the 3x1 translation vector next to it defines the link's length and physical offsets in x, y, and z space.
So how do we actually use that matrix in the real world? Well, for a standard 6-axis industrial manipulator, going through these sequential steps gives you the exact position and orientation of the gripper relative to the floor. We start at the base frame, essentially where the robot is bolted to the floor. And we use sequential matrix multiplication. This is called the chain rule. We just multiply those 4x4 matrices together, joint by joint, until we accumulate the final transformation right at the tool frame.
Which brings us to Section 3, standardizing with the DH convention. Because manually setting up these individual coordinate frames for complex mechanisms quickly becomes a chaotic mess. And on a factory floor, chaos means errors.
To prevent that chaos, roboticists globally rely on the Denavit-Hartenberg, or DH, convention. It's a real lifesaver. We universally plug 4 standardized parameters into a DH matrix template, which instantly generates the correct transformation matrix for any link. You just measure the link length, the link twist angle between joint axes, the link offset along the axis, and the joint angle. Just those 4 numbers. And bam, we've totally eliminated the guesswork.
Now let's flip the script. Section 4, Inverse Kinematics, reaching the target. As a control engineer, let me tell you, this is exactly where real-world operational errors usually begin.
This question perfectly encapsulates inverse kinematics. IK is the absolute core of intent-driven robotic movement. You see, you don't usually tell a robot how to turn its motors. Instead, you tell it where a part is sitting on the assembly line, and the robot has to figure out the exact motor angles required to get its gripper to that precise XYZ coordinate.
But here's the catch. Inverse kinematics is a computational minefield. While forward kinematics gave us one clean, easy solution, a target position in inverse kinematics might have multiple postures to choose from. Think about it like reaching for a cup. You can grab it with your elbow pointing up in the air or resting down near your side. The robot has to make that same choice. And worse, the target might yield no solution at all, simply because it's physically out of reach.
So when we absolutely need to solve IK to avoid a missed target on the production line, we rely on 2 main approaches. For simpler or standard 6-axis robots, we use the analytical approach. This involves exact algebra and trigonometry, and it's incredibly fast. But for complex, highly redundant arms with 7 or more joints, those neat algebraic equations often just don't exist. So we have to switch to a numerical approach, relying on computer algorithms like Newton-Raphson to iteratively guess and converge on the right joint angles.
All right, moving on to Section 5, Differential Kinematics and Velocities. Because look, kinematics isn't just about static, frozen positions.
In a live, dynamic environment, we have to meticulously control the speed of the arm to prevent a physical crash.
This brings us to a highly critical piece of math known as differential kinematics, which is managed by the Jacobian equation. The Jacobian essentially acts as a translator. It maps the individual speeds of the joint motors into the final linear and angular velocity of the tooltip.
Let's break down those variables really quickly. V is the velocity vector of the end effector, theta dot represents exactly how fast your joint motors are spinning, and bridging them together is J of theta, the configuration-dependent Jacobian matrix. Truly understanding this mapping is the ultimate secret to smooth, continuous, and safe motion on a factory floor.
And finally, Section 6, Jacobian, preventing real-world errors. Let's step into the control room for a second and see how this specific matrix is used to prevent disastrous physical failures.
By calculating the inverse of the Jacobian matrix, we essentially create a master control dial that lets us work backwards. The inverse Jacobian allows us to dictate precise motor commands to achieve the exact velocity we want at the gripper. So, if we need a welding tip to move at exactly 10 centimeters per second across the car door, the inverse Jacobian tells the motors exactly how fast they need to spin to make that flawless weld.
But the Jacobian also reveals our absolute biggest operational hazard, singularities. If a robot hits a singularity, it mathematically and physically locks up. Think of a human arm trying to push something forward when the elbow is already completely locked straight. You've lost a degree of freedom, and you literally can't move your hand forward any further without reconfiguring your whole body. In a robot, hitting a singularity results in a total mechanical freeze, which can easily ruin a manufacturing process.
This leaves us with a fascinating challenge as control engineers. Applying this entire mathematical playbook, Forward Kinematics, Inverse Kinematics, and the Jacobian, is exactly how we ensure our robots are always operating safely. But knowing that these dangerous mathematical lockups exist, how do you think we must code and design automated robotic paths to guarantee they never brush up against their absolute physical limits? Keep that question in the back of your mind the next time you see a robotic arm flawlessly execute a complex maneuver. Thanks so much for joining me on this explainer, and keep thinking like an engineer.